very much for the instruction. Next we will have Ganu. I hope my pronunciation is correct. And he's a PhD student at Post-Tech, and who is pushing the boundaries of generative models, especially video generation. And I think he has many works published in top conferences like SIGGRAPH and ECCV. And today he will be sharing his recent research on 3D video generation by diffusion models. Yeah, well, please welcome.
Can you hear me?
Yes, I can hear you.
Thank you for the introduction. And yes, I'm gonna share my presentation. So could you see the presentation?
Yes.
Oh, yeah. So yeah, let me start it. Hi, I'm a presenter Geonung Kim in Post-Tech Computer Graphics Lab, and I'm a PhD candidate. Now I'm going to introduce our recent work, a video from 3D, which will be published in SIGGRAPH Asia 2025. And I'm a first author of this paper, and the others are Chang Han and Sung Cho. So let me start this one. To explain very briefly, a video from 3D takes coarse 3D geometry as an input and generate a scene video as an output. This is obvious as you can see from the name itself, the video from 3D. Now let's look at this in more detail. In this method, user can perform a coarse modeling or just give a coarse model. As you can see in this example, the model has no details like a window frame or a landscape element. Now, it is also possible for a user to simply place a detailed mesh model. In this example, the rocks are the example of the detailed model. And then users give a camera trajectory where they want to render. And finally, users provide a reference image that represents the visual style of the entire scene. After that, video from 3D can generate high quality video that aligned well with the user's intention. So here is a generation result. Okay, now let me talk about the motivation of this work. Let's imagine producing the video we have seen right before using a traditional graphics pipeline. We would first need to create a highly detailed model and then texture it in a way that match the reference image. And insert the writing for a natural looking. And finally, render this. This entire process is extremely time consuming and requires a high level of expertise. So in video from 3D, we enable user to use coarse modeling, not detailed one, and use reference images rather than texturing and lighting. As a result, this method can significantly reduce the resource and task complexity when producing a scene video. So when we address this task, the most straightforward approach would be to use structure conditioned video generation like Cosmos transfer from NVIDIA and or Base. Since this method guide the generation process using the that's condition, and so our task seems to be performed by them. However, it failed to maintain the visual quality. Let's look at a toy experiment. In this experiment, the high quality first frame is given, and the video generation is conditioned on that video. So here is the result. As you can see, the visual quality gradually decreases. It is more noticeable when we compare it with our method. The appearance is too simple and lack of details. There are three main causes for quality degradation. The first is the dataset bias for the camera motion. Most of video dataset has few samples having active camera motion. But when we generate a scene video, like before, we require active camera motion. This domain gap can lead to noticeable quality degradation. And the next is high quality video data set are less common than image data set because taking a video is much harder than taking a picture. And also video frames often inevitably have some artifacts like motion blur. So that's the additional reason to reduce the video data set quality. Lastly, the video diffusion model has to handle more complex tasks like motion modeling and maintain temporal consistency. So this extra work can also make the degraded visual quality. To handle the low quality output of the video diffusion models, our key idea is to mix the strengths of image and video diffusion models. Especially image diffusion model is good at generating high quality frames, but has no temporal consistency. On the other hand, the video diffusion model are very strong at maintaining temporal consistency, although their visual quality is generally lower. So the idea is to generate first the high quality anchor view using the image diffusion model in advance, and then use the video diffusion model to interpolate them. Based on this idea, we introduced SEG module for anchor view generation, the left side, and GGI module for the anchor view interpolation for the right side. The overall framework is the SEG module generate anchor views reflecting the reference style and geometry. And then GGI module generate the middle frames with accurate camera control using warp noise and edge condition. So let me explain these two modules from now on. The second module starts from pre-trained image diffusion model. In experiment, we use Flux model from Black Forest Lab, which is very famous open source high quality image diffusion model. First, to reflect the input geometry, we apply a control net that is trained on edge condition. And then to reflect the reference image as an overall visual style, we use LoRa training that is similar to previous personalization work. Specifically, we fine-tune the LoRa module to the reference image. One little detail in here, we train a LoRa model within the control net, like this. This can reflect the reference style in a better way. The most important part in the SEG module is how it preserves the multi-view consistency between adjacent anchor views. For this, we first wrap the start frame to the end frame using the optical flow that is acquired from the input geometry and camera poses. And then we perform the sparse appearance guided sampling that we proposed. So let's look into the sparse appearance guided sampling. Although the warped view has only partial observation and distorted appearance, like stretched texture, it still has a rough color information and semantic information. To guide this information in generation process, we repeatedly blend the uh, noise warped image to the noise latent during the earlier time step of the denoising process. This can effectively the color and semantic observe the reason by injecting the information into the earlier generation process. The natural following question about this is how we can ensure the multi-view consistency, because the diffusion model has innate randomness, so it is just a rough guidance, so it cannot ensure the strict multi-view consistency. To address this, we take a simple but effective strategy to circumvent this issue. As the name sparse anchor views suggest, our anchor views are placed very sparsely, which means the distance between each anchor view is intentionally large. So this wide spacing gave us a big one advantage. When the camera baseline is large, multi-view generation become highly ill-posed. And interestingly, that actually worked in our favor because the results become less sensitive to the randomness in diffusion model sampling. Simply saying, the more ill-posed the problem is, the larger solution space became. And therefore, the generation becomes less sensitive to the randomness of diffusion model, and the multi-view consistency is naturally maintained. Next, let me talk about the GGI module. We start from the image to video diffusion model to build the GGI module. The first thing to do is to convert it into video interpolation structure. So we just add the last frame as an input. The most important part is actually camera control. For this, we apply a warped noise approach. More specifically, after computing the optical flow from geometry and camera poses, we directly apply warping to the initial noise based on the optical flow. But the resolution of latent space is smaller than image space, so this controller has shown lower accuracy. So to enhance it, we use additional edge condition to handle this. So as a result, we fine-tune the video diffusion model with this added condition and structure to make the GGI module. So here are the additional results. Note that the geometry is detailed one. Video from 3D work well in that case. When anchor views differ significantly, the GGI module naturally interpolate between them. So in this example, our video from 3D framework can make the fire VFX like this. So that's all of my presentation. Thank you for your attention. And if you have any question, please feel free to ask me.
Thank you very much for the presentation. I think it's a very interesting idea, and I'm not an expert or know very little in video generation, and I have a few questions. So, how sensitive is the result to to the diffusion model, I guess you use a pre-trained like image generation diffusion model, right? Have you tried like diffuse different models and see how like whether a better model can have better result at the end for the video?
Oh, sorry, I didn't catch the
Yeah,
question.
my question is that how sensitive is the result to the image generation diffusion model you use?
So your question is how to fine-tune the diffusion model?
For image generation, I guess you use a pre-trained model, or do you
Yes,
train
right.
your own?
For the image generation, we just used the pre-trained model. There was there's no additional training for that. There is a minor additional training for LoRa fine-tuning to reflect the uh, scene style.
Yeah, my question is if you replace it with, have you tried like replace it with different diffusion model for image generation to see if the results changes, like whether a better SOTA diffusion model on image generation gives you better results in your final video?
Mm, okay, I see. Actually, I never tried that because the model flux is actually the best one that I can use in open source. So, and if we use, if we replace it with better uh, performance, I think it'll be, we can achieve better quality. Yeah, naturally.
Yeah, another question is that I wonder like what is like hard part of the video generation, like with what are the edge cases that the diffusion model or your pipeline would fail, like very complicated things, or if the thing changes very much quickly in a short time, would that be a very difficult one to generate, or are there other like difficult cases for the in video?
Oh, yeah, your question is about the fair case. So, yeah, actually the video from 3D has mainly two components. So for each component, there are specific fair cases. And in the case of image generation, let me go back to the, oh, yeah. Actually, this is as you can see, this guidance is have two sparse information. So sometimes the image diffusion model can generate something different. Uh, it is okay. It is okay to generate something different color, but if the image model generates something different semantic, for example, if a diffusion model generates generate the something else rather than rock. In this case, such a case sometimes occur. So in that case, uh, we cannot fail. We can fail to acquire desirable one. Actually, the most fundamental solution for this is uh, we just give the semantic map. In this case, we can achieve this more effectively. But the making the semantic map is also very, I think this is also very time consuming process. So uh, there is a pros and cons when we added that condition in this uh, in this framework. So, and about the yeah, let's talk about the video generation. Actually, I want to show some example, but the video is too fast, so we can notice the fair case. But when we see
Perfect.
this video is very thank you. When we see this video very slowly, actually the temporal consistency is not perfect. There are many flickering. Yeah. Actually, I think the main problem is in the pre-trained video model itself. I mean, uh, yeah, the foundation model has not yet perfect temporal consistency, so we depend on the performance of the video diffusion model. We sometimes fail to preserve the temporal consistency.
Thank you. I think the video looks beautiful to me. And maybe another
Thank
question,
you.
like you mentioned that you use like generated images as like anchor images. I wonder like how frequently you insert such images. Like if you make it more frequent, of course, which requires more computational power, but you like you interpolate more, like using more generated images. Would it like helps in the video generation, give you
The frequency of the anchor view, actually, if there are many, if we generate many anchor view, there are trade-off between image quality and multi-view consistency. So we intentionally reduce the anchor view, and we in our experiment the we just set the amount of correspondence between two anchor view is lower than 20%. Even in extreme case, there sometimes we use the case like zero correspondence.
Okay, thank you. I think that answers my question. Yeah, thank you again for the presentation. Are there like any questions from the
Yeah, hello. So I have some questions about the 3D consistency because I also have lots of experience in 3D generation. So first, I wonder that in the image diffusion generation, it may also create some geometry changes inside of some of the views. For example, here it creates the grass, and sometimes it may create some trees. However, in the warping process, the warping is based on the depth of the coarse geometry, which will not consider this kind of added object. So how do you deal with this kind of warping inconsistency in depth?
Oh, yeah. So your question is the input geometry is actually the courses. So the additionally generated contents may be incorrectly warped to the next view. So it could be your question is this could make some issue, right?
No, so it's more like the warping might not be always precise because sometimes the image generation may create some other geometries. Like for example, here you have grass in the slides you are showing now. But the grass has some geometry, so they should be considered in working, but they are not actually considered in working because you only use the coarse geometry.
It's right.
Will there be a problem or the video diffusion model will be robust?
For the question, it's actually could be a problem, but it is not it it is rarely noticeable in the video generation because Uh, let's see this example. As you can see, the interpolation capability of the video diffusion model is interestingly high. The video diffusion model uh, interpolate two very different images in a way that is very natural. So if there is a inconsistency between two anchor view, but when we generate the after the generate the video, it is rarely noticeable because the video diffusion model very naturally interpolate these two anchor frame. But about your question, if we try to reconstruct the 3D representation like 3D or NERF, it will be the big problem because the inconsistency is very large.
Yeah, but actually in the video, it may still have some temporal inconsistencies. For example, here, generated scene has a tree, and maybe you rotate back, there will be no trees here. Because tree has some geometry, so sometimes you may occlude just in front of the camera. But when you rotate there, it may doesn't occlude because the model didn't notice that there is tree.
Oh yeah, yeah. It could be a problem, but actually, as you can see the example,
Mhm.
I think it is it is an issue subjective. I think it is a subjective property. So uh, in my opinion,
It will be not very severe in most of the cases.
sorry,
So do you mean it will be not very severe in most of the cases?
sorry.
So it will not be a big problem in most of the cases. Do you want to say something like this?
So what I want to say is actually when we try to or we aim to generate really accurate 3D consistent scene when we try this like this, it could be a very big problem. But when we just naturally looking video, uh, it
Not very easy to
we think
notice.
we think it'll be practically fine. Yeah.
Yeah, actually, I think all of the videos just looks very good. So this is why it qualifies the high criterion of SIGGRAPH Asia and SIGGRAPH. So by the way, how do you train your video diffusion model, or you use training free ones?
To train a video diffusion model, we just use the DR3DV10K dataset, which is the large scale sim video dataset.
Uh,
So,
so this 3DV 10K or
uh, sorry, 3D.
yeah, it's also
Sorry,
okay.
I
Maybe let me
forget.
check the paper later. So I
Okay,
believe
okay.
that it's
That
really
was
the case.
actually not about the 3D dataset. It's just a video dataset for static scene.
Yes.
So we actually extract optical flow using the off-the-shelf optical flow estimator and use the edge extractor to to construct the pair data set.
I see. Yeah. Thank you. And maybe due to time constraints, thank you again for your great presentation and great paper. And you can move to the next. Sorry about.
Thank you very much.
So, Geonung, now it's your first of all, thank you for the great presentation again. Now it's your time to introduce the second speaker.
Oh, yeah. The next speaker is Xiang Li, is Zurich, PhD candidate in Zurich. The topic is about the diffusion theory. The name is when scalar geometry lays separation under the manifold hypothesis. This exploring the fundamental success of a square-based model, and Xiang argued that this model implicitly run the data manifold, not for distribution. So yeah.
Okay, thanks very much for the introduction, and I hope you guys can see my screen. So I'm going to talk about our recent work, on diffusion model, and specifically understanding diffusion model under the manifold hypothesis. And this will be this is a work with Dr. Zhebang and Dr. Yaping Xie and Professor Miao He, and we have a group of people from ETH Zurich. And this is going to be a theoretical work that might be a little boring because the slides would contain details of math instead of what's the previous presentation that we have a very nice visual presentation. But I hope that this can provide some insights in also for practice. As we all know that in deep learning, the gap between theory and practice is very large. But however, after we derive this result, we find it very interesting and a bit surprising to us, and might challenge some conventional wisdom. And we hope that we can provide a good view or alternative view of diffusion model with manifold hypothesis. And I hope this talk is going to be interactive. So if you have any question, please don't hesitate. You can just interrupt and ask questions. So I can give an answer. So maybe that helps us to better understand the content. And yes. Okay, so we consider score learning, and it's a core component in diffusion model. I guess many of the audience here are very familiar with this diffusion model formulation. And here is the image from Yang Song's SD perspective of diffusion model. So specifically, we consider that P data is the data distribution at time zero, which is the distribution where your data lies, for example, the image data. And then in diffusion model, we progressively add noise to the image, right? And then after some time t, we have after we have injected the noise of sigma of covariance sigma square, and then we obtain a distribution of p sigma at time t. So here I dropped the t here. Actually, here the sigma should be sigma t. Here I dropped the t here for simplicity. So at time t, we have distribution p sigma, and which is the convolution of p data and some Gaussian noise. This is a simple settings, maybe the simplest setting in diffusion model, and it has a corresponding score function as the gradient of log p sigma. And our goal in this talk is to study what is the behavior as t goes to zero. Like when t goes to zero in the reverse process, diffusion model are trying to generate realistic images, like the images sampled from p data. So we're going to analyze this the arrow between the true score and nerd score and see as sigma goes to zero, also t goes to zero, what is the distribution that diffusion model will recover. So a conventional story is that people expect diffusion model or score learning to nerd the target distribution, that is p data. But however, the empirical evidence is very unclear because it is very hard in general to verify whether you actually recovered your target distribution. Like, of course, for very simple toy data, we might already know the p data distribution, but in practice, this is very hard to verify. And also, typically, this is not the goal of practitioner. Like practitioner often just want realistic images, right? So you as long as we can do a denoising to produce very good looking realistic images. And often we want diverse images, and also exactly recover the data sampling distribution P data is not the goal of many applications. So in this work, our story is that score learning, instead of NER distribution, it actually NERs the geometry structure of the data. So what do I mean by this? So let's consider the arrow between the recovered score function as sigma and the true score. So under the manifold hypothesis, which means that your P data, the support of your P data lies in a low dimensional manifold. So it's a lower dimensional object than the ambient Euclidean space. And now recently, I think there are many works that also pose this manifold hypothesis. Especially like recently, I think Kai-Ming has a work on diffusion model that it's motivated by the manifold hypothesis. P data has a low dimensional structure, and argue that predicting the sample X itself rather than predicting the noise is more efficient. So yes, we assume that the support of P data is a low dimensional manifold. And we discovered that learning the distribution learning is much harder than the manifold learning in terms of your score error. So basically it says that unless your score is not very well, you can, unless this is the case, you cannot recover exactly the distribution. However, for the manifold learning, if you just want to learn the data geometry, learn the manifold, it would be much easier. You require a much, tolerant, a much large score error. And also, score learning must first implicitly learn the manifold before you learn the distribution. So basically, here there are a few implications maybe for what's really happening for diffusion model. So first, people believe that diffusion model are trying to recover the P data as t goes to 0 or sigma goes to 0. But however, learning such an accurate score is usually unrealistic in practice. And maybe in practice, score learning just like a very rough score, and it actually just recovers the manifold. And that is already enough or already explains what we see, because the success of diffusion model is that it can produce realistic images, right? So as long as it lies in this manifold, which consists of all the realistic images, the manifold, and we already have beautiful images, and yeah, it's very hard to say if it actually covers the underlying distribution, the density on this manifold. So I will first give a bit of into.
Sorry, can you maybe repeat the main gist of the theorem? I think I missed the main message. So what do you mean by score learning must learn the manifold? Does that mean does it actually learn it, or does it not learning at the moment? And maybe in order to learn the manifold, there should be score learning.
Yeah, so I think you will see it to clear later when I list the detailed theory. Here I'm just saying that so in practice, score learning might be implicitly learns a manifold, and it actually might not accurately learn the distribution. So basically, to learn the distribution, first you have to learn the manifold. So first you have to make your data, your generated distribution supported on this manifold, and then you can learn the density on this manifold. And we will say that there is a rate separation in how diffusion model can achieve these two tasks. And we argue that recovering the manifold is much easier than recovering the distribution. And maybe this will be clear in the next few slides. Okay, and a bit of intuition on how we can see this. So we consider manifold hypothesis, right? The support of P data is a low dimensional manifold. And then we write down the log density. the distribution that diffusion model are trying to generate at time t, which with a noise scale of sigma. Okay, and we do a Taylor expansion on it, and we say that the leading term of order 1 over sigma square is the distance function to the manifold. So basically, this term is given x, the distance of x to the data manifold, right? So it contains purely the geometric information, and it does not contain anything about p data. So as we can see, that this tells us that as sigma goes to 0, your data will your distribution will gradually concentrate on the manifold. So here's a visual example: is the manifold is a unit circle on 2D. Okay, and this term, this leading term, very strong signal, will determine the support of the limiting density. And then we see that the information about p data appears in the theta 1 term. So this tells us that if you want to recover p data, that if your task is to know the target distribution, you have to know the score very accurately to to an error of small o1. If you can just if you have an error that's of order big O1, then the information of p data may be like contaminated by your error. And this level of information, the theta 1 term p data, could be not accurate. So you will not be able to recover the data. But however, the geometry information lies on a like stronger signal, lies in a larger term as sigma goes to 0. So basically, here it tells us that to accurately know the p data, first you have to know very well the geometry, right? And then p data lies in a lower order term. So what's this our theory
about the
form?
notation? So is the first term here the projection distance, or what is it? So
yeah, the projection in
projection
Euclidean
distance.
space.
I see. Yeah, that was my question.
Yeah.
Thanks.
Okay, good. And so our exactly theory states as this. So under the manifold hypothesis, we denote our score error as E sigma. So if we have E sigma as order of small o1, sigma goes to 0. As we can see from our intuition that we already recovered the geometry term and also the density term. So we can have that the distribution generated by diffusion model will converge to p data. So this is the success case of diffusion model recovering p data. But however, the requirement is very restricted. So normally in training, this is unrealistic because we often observe in training as sigma goes to 0 or t goes to 0, the training is very unstable. You cannot obtain a very accurate score. However, if we have that the score error is of small o sigma to -2, then we can prove that the generated distribution already concentrated on the manifold. So it will the support of this generated distribution is the manifold, right? And this allows a much larger tolerance of the error. It can actually diverge as sigma goes to 0. And we also provide a negative result, a lower bound, such that if you know your score only as omega 1, then you can have arbitrary distribution on your manifold, which means you cannot actually control what is the distribution generated on this manifold. And this tells us the story that actually recovering p data is very hard in practice. And before you recover p data, if you know your score only roughly accurate, which we believe is the practice, and you actually first recover the manifold. You have a distribution that's supported on the manifold, so you already have very realistic and beautiful images. Okay, and then this motivate us to think that is there a way that we can design algorithm to generate a meaningful distribution on the manifold given a not very accurate score? So here in this result, existing like diffusion model, if you have less accurate scores, you cannot control the distribution generated. But from our intuition, we see that there's a strong signal on the geometry, right? Maybe if we don't care about the data density, if we just not target to produce P data, maybe we can do better in recover the geometry. So our next series states that if we run this tempered Langevin algorithm, right? We temper the temperature parameter in the Langevin dynamics with a NERSC score, and we can recover the uniform distribution of the manifold. And the error of the score tolerance can be O small o sigma to a beta for some beta greater than -2. Basically, your score should be smaller than the leading geometry term. And for diffusion model, in this case, it only gives you unknown distribution of the manifold. But with our tempered Langevin algorithm, you can probably converge to a uniform distribution on manifold. This is helpful in like many cases if you don't want, like if your P data is a biased data set and you want to have unbiased or principal exploration on the manifold to give you like more diverse data, you want to like explore different diverse images, and this could be very helpful. And importantly, this is under the weak score error requirement, and it gives you a meaningful distribution. And this is what we mean to an explicit manifold learning. So in overview, that we have first in existing diffusion model that we the target to know the density on the manifold, and it requires a very accurate score learning, usually unrealistic. And we discovered that there's a sharp risk separation that if you only narrow your score to some roughly, right, even if it can diverge as sigma goes to 0, and you can already recover the support in diffusion model. But however, we cannot control what is the density generated on that manifold. And then we propose a paradigm shift that we think if our target from the beginning is to learn the geometry, learn the uniform distribution on the manifold, then given a very coarse score error, we can already do this. The same rate as for diffusion model where it generates unknown density. We can already target to learn exactly the geometry. To be able to actually do uniform sampling on the manifold, we actually nurse most of the geometry property of the manifold. Like it gives us geodesics or even Laplace operator on this manifold. So here's the toy example that we tried test our theory on very simple unit circle embedded in 2D, and we see that in previous work they cannot generate P data if given a not accurate score. But however, in using our tempered Langevin method, we can robustly recover the uniform distribution. The uniform distribution with respect to the Riemannian volumetric on the manifold. And we are thinking how can we plug in our tempered Langevin dynamics into existing diffusion models that can help us generate more diverse and samples. So in diffusion models, there's a common, I think it's a popular framework called predictor-corrector framework, which is basically in the reverse process. In each reverse step, we have an inner loop that runs Langevin dynamics as the corrector. Right? And we can simply replace this with our tempered Langevin dynamics and hope it can because we have proved that the stationary distribution of this Langevin dynamics is a uniform distribution as sigma goes to 0. So we can hope that this could guide the samples to more uniformly distributed on the manifold. Okay, and this is just one-line modification in existing diffusion model. You don't need to actually retrain a diffusion model. Right? Here the score is already given by a pre-trained diffusion model. So, and I feel experiment results we actually, but the experiment here is quite preliminary. We tested on stable diffusion 1.5 and see that in terms of the image quality and also the diversity, we have some improvement over simply predictor, corrector, or DDPM model. Okay, cool. So to conclude, so under manifold hypothesis, we proved that score learning first learns the geometry structure before learning the full distribution. And this can provide an alternative explanation as why score learning or diffusion model is so successful in practice. It might not already recover P data as many people would expect it. It might not only makes the data to be concentrated on the manifold, and which already satisfies our requirement of generating realistic images. And there are a few limitations and future works in this work. First, the relaxation of some technical assumptions. Currently, we assume the score error to be in the L infinity norm, and a more realistic case may be in the L2 norm. And also, it would be nice to consider statistical complexities as how many samples are required to train such an accurate score. And also, for uniform distribution generation, we consider Langevin dynamics, which is purely continuous time. And it would be nice to have some discrete time analysis for this algorithm. So yeah, thank you for listening to this talk, and I'm happy to answer any questions.
Oh, thank you for your great presentation. Actually, I'm not really familiar with the theoretically rich content like that, so it is hard for me, but I try my best and ask anyway. There's several questions. The first question is, from what I understand, the assumptions and theorems in the paper are mainly focused on small sigma values. So, and in your method, in your final method, is there a specific sigma range where your approach is applied only for the small sigma values?
Yeah, this is a good question because I have to admit that in this work, lots of results are asymptotic and sigma goes to 0. And actually, this is a region maybe many people cares about this. This is a region where t goes to 0, right? As the diffusion model are about to recover the P data. But in practice, many people also argue that maybe there are some distribution or mass allocation before sigma goes to 0. For large sigma, there are already something happening. But yes, in our theory, that would be very complicated. In our theory, we just consider asymptotic behavior as sigma goes to 0 and only consider this small region. And in practice, usually in diffusion model, you run this inverse process to a very small sigma, right? I don't know, 10 to the -3 to the -2, something, right? And also for our tempered Langevin dynamics, we just fix a very small sigma, 10 to the -3, and run this Langevin dynamics until convergence, and to generate uniform samples on the manifold.
Oh, thank you very much. And my next question is, I understand about I agree with the final method can improve the diversity of the generation process, but I just curious about how the visual quality can be improved. I mean, the goal of the method is make it unbiased, so not improve the quality. So in my opinion, relaxing the biasing is not related to the visual quality improvements, but your experiment showed that noticeable visual quality improvement. So I just curious about that.
Yes, I think the improvement on the feature quality might not be well explained by our theoretical framework, but yeah, and here, so for example, here in this experiment, so we for the P theme is actually to measure the similarity between the prompt and the generated images. So basically, we compute the clip score and to compute the average clip score between the prompt and the images to see how, like, whether it's consistent to the prompt. And then for the ISIM score, which is the pairwise image like clip score. So a lower this score, so which means it's more diverse. And we can see for the image quality, it's not always the case that our framework gets better performance. And yeah, it would be interesting to investigate whether this why this can actually help in many cases where the image quality becomes also better. Yeah, but I have to admit that our current theory only address that we try to make the image more diverse.
Oh, thank you. And last, a very short question. I'm wondering whether you tried use other standard metric like FID, which is commonly used in image generation model.
That we haven't. So this is quite preliminary experiments, and yeah, I believe our major contributions in theory, and this is to just showcase how this can be applied in practice and show some improvements. And yes, we haven't tried the FID score. So all the score reported here is the clip score.
Oh, thank you very much. This is.
I have a follow-up question. So eventually, it's not actually a follow-up question. So my main question is, the final method that you proposed eventually is essentially adding more noise or adding more weight on the noise term during the, how do you call this, like modulation? So the method itself sounds very simple eventually. I wonder if this is something that people do in this domain, in practice anyways.
I think what people has some like simulated leading like method that also turns this temperature parameter and also like temper the longevity is not a new thing in this field, but it really depends on like how you temper this temperature score. Here we have a very specific temperature, such that when sigma goes to 0, the stationary distribution of this dynamics will converge to a uniform distribution. And this is something that we haven't seen before, like because in previous work, although they have some tempering, but they are also trying to target the p data distribution, right? And also I can give a very like simple intuition on why this could work mathematically. So after you applying this sigma to the power of alpha, and we can see that the leading geometry term still is the leading term. And as long as alpha is smaller than 1, right, and sigma goes to 0, this term still stands out, and which pushes all the densities towards the manifold and does not introduce any side information like the density. And otherwise, the density information after multiplying this sigma to the power of alpha, it becomes a small O1 term. So it does, as sigma goes to 0, it does not contribute to the limiting distribution.
Yeah, I understood it. Thank you so much for the great intuition. I have some follow-up questions, but I'll ask them on Slack.
Yeah, sure. I'm very happy to see that people are interested in it.
Yeah, it's super interesting. Thank you so much.